Hello. Today we're going to learn how to find the derivatives of inverse functions. We're going to start off with the inverse trig functions, and then we're going to just generalize how to find the derivative of a general inverse function. And then we're going to use this rule eventually to come up with the derivatives of the logarithmic functions down the road. So let's get started. So like if we think about inverse functions, probably the easiest one to think of might be, how about we'll start off with a nice inverse trig function. Y equals the inverse sine of x. Okay? Now, first of all, before we even get into this, you need to understand what is this function. Okay? This is an angle function. This is the set of angles whose sines are x. You put in sine values and you get out angles. Okay? So we got to make sure we understand the inverse sine function. If I asked you to draw a picture of what the inverse sine of x looks like, maybe you could draw a triangle and say, okay, let's call this the inverse sine of x, right? So if this angle is the inverse sine of x, his sine value has to equal x over 1, which would make the other legs of the triangles look like that. Okay, so that's what the inverse sine of x looks like in terms of the geometry. We could look at a graph of this function too, but I'm not necessarily interested in that right now. So I want to know at this point, I want to know the derivative of this. I want to know what dy dx is. Okay, I'm writing right across my face. I just realized that. So I want to know what dy dx is. Okay, so let's figure it out. Okay, so we're going to start off with y equals the inverse sine of x. Okay, and now here's the thing. Is there another way that you could write this function that it tells the same story? Y equals the inverse sine of x. And the answer to that is yes. This statement right here, nope. Back that up. Not that statement, dummy. I just rewrote that. This statement right here and this statement right here are the same. They both tell the same story. Y is the inverse sine of x. Oh, that means x is the sine of y. That's like saying 2 squared equals 4. Oh, the square root of 4 equals 2. These two statements are telling the same story, right? These two statements are telling the same story. All right, so now what we're going to do is we're going to look at the story being told this way, and we're going to differentiate this. Differentiate is a fancy word for take the derivative. So we're going to take the derivative of this equation, both sides, with respect to x. Okay? We're going to take the derivative of both sides with respect to x. Okay? So now, the left side, if I differentiate x with respect to x, hopefully you're thinking, I got that. That's equal to 1. Okay? But the right side's a little bit trickier. Okay? The right side is a little bit trickier because this right here is actually a chain rule problem. When I take the derivative of this with respect to x, you might be saying, wait, there ain't no x in there. You're right. But there is an x in there hidden because y is a function of x. Okay? So when I take the derivative of this function right here with respect to x, I'm going to take the derivative of it with respect to y first, and then multiply by the derivative of y with respect to x. That's the chain rule. Now, I know I just said a whole lot of stuff real fast, and you're probably like, huh? What did he just say? So let me write it down. So I take the derivative with respect to y first, and then I multiply by the derivative of the inside. Now, what's the derivative of y with respect to x? It's dy dx, okay? And guess what? That's the derivative I'm looking for. I wanted to know the derivative of y with respect to x. This is sort of like a backdoor approach here, sneaky attack to figuring out what this derivative of this inverse function is. So if I solve this for dy dx, I get 1 over the cosine of y. Okay, 1 over the cosine of y, which isn't necessarily that convenient of a form. So maybe we're going to change that up a little bit, and I think we'll go back to that picture over there. I'm going to rewrite it right over here, so I'm going to say 1 over the cosine of y was equal to dy dx, right? And so now I'm going to say, well, what was the cosine of y? Well, what was y? Y was the inverse sine of x. And now you might be looking at this saying, wait a minute, that looks weird, but this is a function of x now, right? I mean, it is weird. And you got the cosine of the inverse sine of x. And this is what I was saying earlier. You have to understand the inverse sine of x is an angle, okay? 1 over the cosine of that angle. So go over to this picture. There's the inverse sine of x, the angle. What's the cosine of that angle? What's the cosine of this angle right here? Well, SOHCAHTOA, adjacent over hypotenuse. So it's 1 square root of 1 minus x squared over 1. So 1 over that is going to equal 1 over the square root of 1 minus x squared. Okay? So there is the derivative of inverse sine of x. The square root 1 over the square root of 1 minus x squared. Okay? So what we did first, we kind of summarized this, and we're going to do another example here, is we took the statement originally, the function that we had, and we rewrote it. We rewrote it in a different way, but we're telling the same story, an equivalent way. Then we differentiated that with respect to x, and then right here, friends, when you write this in pink, right here we use the chain rule. Chain rule. Okay? Right there is where we use the chain rule. Okay? And then we solve for dy dx. Okay? So I'm going to pause this, erase this, and then we'll come back and try another one. Okay, so here we are back. Got a new function. Y equals the inverse cosine of x. Okay, let's find the derivative of this function here. So I want dy dx. Okay? And I'm using this notation here rather than f of x, just because it actually is probably a little easier. If we started using f, then when we switch this around to tell the story another way, it gets a little clunky. Maybe with the tangent one, when we do the next example, I'll show you what I mean by that. So the first thing you got to do is you're going to say, wait a minute, y equals the inverse cosine of x. I know that's an angle. I think it'd be a really good idea for you to draw over here a picture of that angle. Draw a picture of that angle. Draw me the inverse cosine of x. It's right here. It's right there. Can you label the sides of that triangle? Here he is. Hello, inverse cosine. He needs to have a cosine that's equal to x. Adjacent over hypotenuse, which makes this side 1 minus x squared. Which, yes, the legs of that triangle are labeled exactly like the legs of the inverse sine triangle. And that's because sine and cosine are the same thing. They're just, the sine of one angle is the cosine of a complement. So it's like if we put the inverse sine of x right here, the triangle would be the same. Okay. So anyway, let's go back to this. So rewrite this statement right here so that we're telling the same story. How about x equals the cosine of y? These two statements are telling the same story. So now let's differentiate this with respect to x. Okay. Now when I put this d over dx here, you have to look at that. You have to think of that like a command. Thou shalt take the derivative with respect to x of, and then whatever's inside the parentheses or the brackets. Okay. This is like a command. Technically, we call it an operator. It's like a command. Okay? So, what's the derivative with respect to x of x? 1. What's the derivative of x with respect to x of cosine of y? We're going to use the chain rule here. It's negative sine of y times the derivative of y with respect to x. Okay? Now, don't just go sticking a dy dx there just because, oh, it seems like we just take the derivative of that and then put a dy dx at the end. Yeah, that's what you're doing. Understand why is it that you're doing that? Because you're taking the derivative of this whole thing and then you're multiplying by the derivative of the inside. And the derivative of the inside with respect to x is dy dx. Okay, now we solve this for dy dx. And there we go. You can see I changed pens on this one so I could fit it all in one line. So now I have dy dx is 1 over negative sine of the inverse cosine of x. Okay? So now, go to the triangle. Go to the triangle. What is the sine of the inverse cosine of x? So there's the inverse cosine of x. There he is. What's his sine? Opposite over hypotenuse. Oh, look at that. It's the same as it was before. But there's a big difference here. Okay, because this one's negative. So the inverse cosine's derivative and the inverse sine's derivative are the exact same, except the inverse cosine's negative, which follows suit because the derivatives of all the cofunctions are negative, remember? So that kind of is nice. So now we've got the derivative of the inverse sine function, and we've got the derivative of the inverse cosine function. Stick around, we're going to do the derivative of the inverse tangent function. Oh, we're back. Caught me drinking some coffee here. Okay, so now we're going to take the derivative of the inverse tangent function. Now you notice I used f of x here instead of y. This is to show you just another way of looking at this using different notation. And maybe you'll find that dy dx notation is easier. Maybe you'll find this is easier. I don't know. So here we go. Ready? So the question is, first of all, let's draw this angle. Okay, let's draw that angle. Okay, the inverse tangent of x. Can you draw a picture of that angle? Okay, here he is. Hello, inverse tangent of x. But he's got to have a tangent that's equal to x. So opposite adjacent. Which means this side right here is, by Pythagorean theorem, Pythagoreus. Okay, I don't know if you saw that TikTok video about math. I'll show it to you sometime. It's really funny. But it's actually not just funny. It's really, really interesting. I would love to have a conversation with you guys about that when we come back, hopefully soon. Sorry, that's a little total sidetrack. I should just edit all that out. Anyway, let's get back on this. Let's talk. Rewrite this statement right here, but tell me the same story, but write it another way. So that's going to say that x is equal to the tangent. Oh, I'm not using y. I'm using f of x. Okay. Now, by the way, in this particular case, I want f prime of x. That's what we're after, right? So here we go. What's our next step? Once we've told the story another way, we differentiate this with respect to x. So we're taking the derivative of both sides with respect to x. So the derivative of the left side, 1. The derivative of the right side, okay? Here's where the chain rule is going to come in. So we got to say, okay, what's the derivative of the tangent function? Okay, if you think back, the derivative of the tangent function is secant squared. So it's going to be secant squared of f of x. And then we're going to multiply by the derivative of the inside. And what's the derivative of the inside? How about we just call it f prime of x. So now we're going to solve this for f prime of x. Okay. And then I'm going to go back and resubstitute. 1 over the secant squared of, what was f of x? Inverse tangent of x. So now, remember, the inverse tangent is an angle. So what's the secant squared? Let's first find the secant of the inverse tangent of x, okay? So secant of the inverse tangent of x, what is that going to be? Well, secant is going to be 1 over the cosine. So the cosine of the inverse tangent of x is 1 over radical 1 plus x squared, adjacent over hypotenuse, right? So the cosine squared, or let's back up. So if the cosine is 1 over radical 1 plus x squared, then the secant is radical 1 plus x squared over 1. So the secant squared is just going to be the radical just squared, so 1 plus x squared, right? And there's the derivative of the inverse tangent of x, okay? So some people might have a trouble how I went from here to here, so I'm going to go back and re-explain this to you real quick. If the cosine is 1 over this, adjacent over hypotenuse, the secant is hypotenuse over adjacent, so that's why we have here. And then the secant squared of the inverse tangent of x is just going to be 1 plus x squared. So 1 over that is here. Okay? So that's the derivative of the inverse tangent function. Now, let's go ahead and summarize these. I'm going to just draw a little line here. So we have the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. We have the derivative of the inverse cosine of x is negative 1 over the square root of 1 minus x squared. And we have the derivative of the inverse tangent of x as 1 over 1 plus x squared. Okay? So you're probably going to need to memorize those three at some point. I might have you derive the other three, inverse secant, inverse cosecant, inverse cotangent, just for fun and practice. But you probably want to memorize those three. Now, in the next part of this video, after we erase the board, we're going to derive a formula that is sort of a formula that can find the derivative of any inverse function, a general inverse function. So stay tuned. Okay, so here we are, we're back. So I've just got a random general inverse here. Y equals f inverse of x. F inverse and f, those can be anything we want. Okay? And we want the derivative of this. Okay? A lot of times how you'll see this is like f inverse prime. Okay, you might see it written like that. So we want dy dx, okay? So here we don't have a triangle here or anything, but we've got to tell this story. We've got to rewrite this story another way. How do we do that? Well, if y equals f inverse of x, then x equals f of y. Okay? X equals f of y. And now we're going to differentiate this with respect to x. And the left side is 1. Notice the theme here. What's the derivative with respect to x of f of y? Well, it's going to be f prime of y times dy dx. All right? And now we'll solve this for dy dx. I have that. And then go ahead and clean this up. F prime of, what's y? F inverse of x. Okay? Now, real quickly, I want to show you how this formula works with one that we already know. Okay? So let's just say the inverse sine. We'll start off with the one we started with. If we said y is the inverse sine of x, right? Or that's like saying f. Let's do it like this. Make more sense. F of x is sine of x. F inverse of x is inverse sine of x, right? So I want to know what the derivative of this is. Well, what's f prime? That's cosine of x, right? So we said that the derivative of f inverse of x is 1 over f prime of f inverse of x. So f prime was cosine, so that's 1 over cosine of f inverse of x. And if you think back, we actually had that right there when we did the inverse sine function. Go back and look at your notes, you'll see it. And then we drew the triangle and figured it out. Okay? So I'm going to erase this, and then we're going to do a couple of examples, show you how these babies work, and then you should be good to go. Okay, so here we go. I've got a function here. F of x is inverse sine of 5x. I want the derivative of this function. Okay? I want f prime. Now, friends, we're not going to go through that process again that we just went through, where we told the story another way. We could, but we don't need to, because we now have a formula for the derivative of the inverse sine function. Okay? The derivative of the inverse sine function, we wrote it down a second ago. The derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Right? And I'll just go ahead and write it again. Okay? So now, because I have that formula, I can just own that formula and then use the chain rule right here to figure this out. So the derivative of inverse sine of 5x is going to be the derivative of the whole thing. So I just put the 5x in there instead of x, and then multiply by the derivative of the inside. And there you go. We're done. Don't have to do anything else. Just leave it like that. Okay? Let's try another one. How about f of x is the inverse tangent of x squared minus 3x. Okay? Derivative of inverse tangent of x squared minus 3x. So here we go. Now the only way this works is you got to know that formula. You got to know the derivative of the inverse tangent function. Maybe we'll write it down again over here for the second time. The derivative of the inverse tangent function is 1 over 1 plus x squared. So now if I want the derivative of this baby, I just say, okay, that's 1 over, I treat this guy like the x, take the derivative of the whole thing, and then multiply by the derivative of the inside. Done. It's that simple. Okay? Let's try one more, just for funsies. How about, I'll use another letter here. G of x is inverse cosine of, how about we do this? How about inverse cosine of tangent of x? Whoa. Okay? What's G prime? I'm going to draw it over here, because I'm running out of room at the bottom there. In order to take the derivative of this guy, you need to know that formula for the derivative of the inverse cosine function. The derivative of the inverse cosine function is negative 1 over the square root of 1 minus x squared. It's a kind of a big radical there. Okay? So here we go. Ready? What's the derivative of inverse cosine of tangent of x? Well, it's negative 1 over the square root of 1 minus tangent of x squared times the derivative of the inside. What's the derivative of tangent of x? Secant squared of x. Done. How about that? Okay? So you could clean that up if you wanted to, but just leave it like that. I'm fine with that. Okay? Okay, I'm going to do one more example. I'm going to erase the board, give you an example of where we're going to use that formula that we talked about a second ago. Okay, we're back. So here I've got a table of values here. I've got a table of f values, and I've got a table of f prime values. Okay? And the task is I want the derivative of f inverse of x when x equals 1. Okay? I want the derivative of f inverse of x when x equals 1. That's one way of representing that. Another way of representing it might be this. F inverse prime of 1. Okay? So what I'm really after here is I want the slope of the tangent to the inverse function when x equals 1. Okay? Now, if you notice, I don't have a table here for f inverse. Okay? I just have f values. But if you actually understand inverses, you do have a table of f inverse values, because you have f inverse of 2, which is 1. You have f inverse of 3, which is negative 1. and you have f inverse of 1, which is 0. So, here we go. Now, the derivative of f inverse at 1, if we use our formula that said that the derivative of f inverse of x is equal to 1 over f prime of f inverse of x. So the answer that we're looking for, the derivative of f inverse of x when x equals 1, is going to be 1 over f prime of f inverse of 1. So that's going to be 1 over f prime of, what's f inverse of 1? Well, I look at my chart here and I said, well, when x is 0, y is 1. Or when x is 0, f is 1. Which means f inverse of 1 is 0. So the answer to my problem here is going to be 1 over f prime of 0. And then I go over here to back to my chart, and I see f prime of 0 is 3. So this is going to be 1/3. Oh, that's cut off. Hopefully you can see that. 1/3. Okay. Now let's go ahead. I said this was, we said this is the slope of the tangent line to f inverse at the point x equals 1. Let's just knock out that equation of the tangent line. Ain't no thing. Okay, because in order to write the equation of a tangent line, you need a point and a slope, right? So we're going to do the equation of tangent to, let's get some ink here, to f inverse at x equals 1. So what's our point on f inverse? F inverse of 1 is 0, and our slope is 1/3, so it's going to be y equals 0 plus 1/3 times x minus 1. Okay? So that's how you take the derivative of an inverse function, but we should know the derivatives of inverse sine, inverse cosine, and inverse tangent. We should have those sort of committed to memory at some point, and then be able to use the chain rule to take derivatives of various inverse trig functions. We won't have to go through this whole development stage where we do this backdoor approach. We won't do that every time. Once we have the formulas, we're going to go. So take care. We'll see you soon.